Welcome to today's webinar with SCA. We've got Dr. John Lorenz and Scott Cooper on the importance of natural fracture type in controlling reservoir permeability. Before I introduce Dr. Lorenz and Scott Cooper, I'd like to remind the audience that you're muted, but you may ask questions during the GoToWebinar presentation using the features there on your dashboard. We'll cover most of those questions at the end of the presentation. So the presenters that are joining us today are instructors for SCA. Dr. Lorenz got his education from Oberlin College, University of South Carolina, and Princeton. Then he worked for the survey in Louisiana and New Mexico and for Sandia in the Piceance Basin. He's been a consultant since 2007. Perhaps most notably, he served as the president of the APG 2009-2010, and he's published numerous papers on the topic of fractured reservoirs and won several awards through APG. He works closely with the oil and gas industry and provides field trips, hands-on experiences with core analysis, and he's done this in numerous locations around the world. He works closely with Scott Cooper. Scott started his career with a first degree from South Dakota School of Mines and then New Mexico Tech. And from there he was working at Sandia as well in the DOE Research Lab, working on a number of applications with fracture studies and EOR applications. And he and John have been working at Fracture Studies LLC together on these types of fracture reservoir issues. So together they present a class for SCA that's entitled Characterization of Naturally Fractured Conventional and Unconventional Reservoirs. This year it's offered in April in Houston, and in October it will be held in Midland in the public venues, and of course it's also available to be brought to your own location in an in-house class. So if you would like to register for one of these two courses, here's some information that you can contact SCA to set up that training. This is part of the series that we've been conducting of free webinars for SCA instructors presenting samples of the material that they will cover in their classes. Coming up, we have Steve Sonnenberg. On February 7th, he'll be talking about exploring for mudrock reservoirs. And then we have Steve back again at the end of February, February 27th, on unconventional petroleum systems from deep basin to tar sands. Then we will hear from Jennifer Miskimmons in March. She'll be talking about fracture conductivity. And Raymond Woodward is also scheduled in March for a talk on geostirring. And as a reminder, in addition to training, SCA provides consulting, direct hire projects and studies as well. So before we start today's presentation, we have some polls that we'd like to conduct to see who's here in our audience. So I'm launching the first poll, and this will tell us a little bit about your primary discipline. Just a quick look, it looks like we're getting a pretty good balance between geoscience, petroleum engineers. We have a few petrophysicists in the crowd. Looks like most of you have voted. So I'm going to go ahead and share those results. We've got maybe 2/3 geoscientists, 1/3 petroleum engineers, and a smattering of petrophysicists. And then the next poll we would like to ask you is about your years of full-time experience. So please give us some feedback about how many years of full-time experience you have in the oil and gas industry. Looks like we've got a wide range of different experience types. Quite a few of you over 30 years experience, but pretty good representation in the other levels as well. So let me go ahead and close that poll and share those results. Looks like 41% have over 30 years experience, and we cover every other demographic except the new hires. We don't have anyone with less than 1 year experience in the oil and gas industry. So thanks for sharing some demographics for us. So again, remember, we're going to start the presentation. I'll hand over the presentation to John Lorenz and Scott Cooper. As you pose questions to them using the dashboard, make sure you address it to one of them so that we'll know who can start answering the question. They're in a room together, so they'll pass the baton if needed. And after today's webinar, you will receive a link to a recording of this webinar. You'll get an evaluation form and a link to registration details for the workshops they have scheduled in April in Houston and in October in Midland. So without further ado, I'm going to give presentation rights to you, Scott, and let you take it over. Thanks.
Looks like our instructors may have had a technical difficulty.
Okay. All right, so we'll give them a couple of minutes to pick it up there. And again, the classes are scheduled in Houston, April 16th through 20th, and in Midland, October 15th through 18th. And the class is entitled Characterization of Naturally Fractured Conventional and Unconventional Reservoirs. And they have in that class a sample of cores that they bring. I think there's 50 core samples that are a teaching collection that they use in the class. So they will bring that information either to our office here in Houston or to your office if you want to have the presentation done in-house.
I believe he's gotten reconnected. Let's see.
Okay, yeah, we
John,
just
can you hear us?
connected here.
Looks good.
Somehow Scott's computer just locked up.
Okay, I'm making you the presenter, John.
Okay. All right. Can you see our web? Can you see our...
You'll need to use the show screen button. Looks like a monitor.
Okay.
There we go.
You're up.
Okay. So apologies for the minor glitch there. What we'd like to do today is to give you some insights in why it's important to differentiate between shear and extension fractures in a reservoir. We've got one-dimensional data from core, from image logs, basically vertical data set. And if we can maximize the information that we can get from these different vertical data sets, we can begin to build up a three-dimensional conceptual and even a three-dimensional quantitative model of the fracture-controlled reservoir permeability that we have down in the subsurface. So it's very important to be able to show the difference between the extension fractures and shear fractures. You've got a view here on the left of a extension fracture with a plume structure, and on the right it's a shear fracture with steps. And Scott will be showing you some of the significant differences that you can use in the fractography, the surface features of these different fractures that you have in cores, to develop a conceptual model of what your three-dimensional fracture network looks like from one-dimensional data. So the difference between extension and fractures and shear fractures really is kind of significant. What we're looking at is a difference between a poorly connected reservoir set and a well-connected reservoir set. Whether you've got significant anisotropic drainage in your reservoir or reasonably well radial drainage from intersecting fractures. And it also depends on whether your fracture system is parallel to your maximum compressive stress in your reservoir or oblique to it as to the behavior of your fractures during drawdown and how these natural fractures interact with the hydraulic stimulation fractures. So it's important to make the difference, and Scott will take over from here and start talking specifically about some of these differences that we can see in the cores.
Hello, everyone. Name's Scott Cooper, and I would like to discuss, starting with how do we actually differentiate these different fracture types. And one of those ways is by physically looking at the fracture surface so that we can look at the fractography, the surface structure on these fractures, and tell them apart. I need to quickly swap presentations here, if I can. And there we go. And the fractures, looking at the surface of these, we can see a plumose structure, and that plumose structure propagates from near the handle of this hammer from left to right, and that's showing the direction of fracture growth. These arcuate lines are actually showing arrest lines, where areas where the fracture actually stopped growing or slowed down in growth. And these are very diagnostic of extension fractures. And that's the first type we're going to talk about today, are the extension style fractures. These are generally parallel in strike when we're looking at extension fractures, and we can see that from both the image log on the right and the subsequent Rose diagram on the left. They generally normal to bedding and very parallel in strike, which has some very interesting production implications that we'll get into. As we look at an outcrop here in New Mexico, we're actually flying a plane. John's flying, and I'm leaning out the window taking a photograph of this Dakota outcrop. In the center of it is a little red cylinder. That's a supposed well being put into this particular reservoir. You can see that all of these fractures are nearly parallel to each other. And then out here in the desert environment, many plants tend to grow along the fracture trends in this case. And these little scrub junipers are about 2 feet in diameter. Next, let's assume we're going to start producing from this single well, and we're going to see a fairly highly anisotropic drainage pattern form that's going to be parallel to the natural fracture trend and is going to be very narrow against that trend. In some reservoirs, this ratio is up to 1,001, recorded in the Permian Basin. Now, if we actually put in 2 wells along trend, initially you're going to see an awful lot of interference and only very poor sweep of this area. If we go into secondary recovery, again, the sweep is going to be very narrow in here, and we're going to get very quick breakthrough. If the well here in the upper left is our injector, it's going to go right along the fracture pass directly into our producing well, and we get very poor sweep. These are concepts we want to keep in mind as we go forward. Now, if we've done our homework and we know what the orientation of the fracture trends are, we can design our reservoir to have better sweep in this same situation. We offset the wells across our natural fracture pattern, and then our sweep is much better through the matrix, and we don't have an early breakthrough from our injector well to our producing well. Conceptually, looking at a reservoir like this, we have very parallel fractures that don't actually intersect very well. The maximum horizontal permeability, K big H, will be parallel to our natural fracture trend and in that fracture. And across the trend, or normal to it, the permeability will actually be the matrix permeability. Now let's look at another type of fracture, and these are shear fractures. We're looking at a conjugate set of shear fractures in an outcrop here in New Mexico. These are dipslip conjugates. Again, we want to look at the surfaces of these fractures that really help us decide whether they're shear or extension. And here's the surface. We don't see any plumes. We don't see any arrest lines. What we see are steps. You might also see some slicken lines or smeared out crystals on a surface like this. These are very diagnostic of shear fractures. And as you want to note, these things are actually parallel in strike, these dip-slip shears, much like the extension fractures by looking at the Rose diagram on the left. But as we look at the FMI image on the right, you'll notice they have opposing dips. And in areas like here and here, they are intersecting in the subsurface. So while they're parallel in strike, they actually intersect. The next slide shows this again in an outcrop from Utah. These are dip-slip conjugate shears, and the strike is in and out of the photograph here, and they're quite parallel, but we can see that they actually intersect each other along the cliff face. And the red line here helps highlight that interconnectivity between all of these different fractures. So we actually have some lateral connectivity of these fractures. And that's very important when we go to look at these as how they're moving fluids in our reservoir. So conceptually, looking at these, we have fractures that are still parallel to the maximum horizontal compressive stress. However, the matrix permeability across this fracture set is less than the matrix permeability or the fracture permeability across this. Parallel to the fractures is the highest amount of permeability. So we have added permeability across these fractures. And another type of conjugate shears we can get, besides dip-slip conjugate, are strike-slip conjugate shears or thrust-slip conjugates. In this case, we're looking at strike-slip conjugates, and we're out in the field wearing our, obviously, company-approved field boots and very safety conscious. But we want to look at the side surfaces of these again, and on the sides, they will have some of those steps and slicken lines, indicating that these truly are shear fractures and not two sets of extension fractures. Conceptually then, looking at a system like this, we have two orientations of fractures. One here is off to the left and one going back off to the right. They intersect at an acute angle. That acute angle is bisected by the maximum horizontal compressive stress. And that is the direction in general of our highest permeability. Across our fracture trend is the minimum, and it's still better than the matrix permeability because obviously we're intersecting a lot of fractures in this case. So let's look at a real world example of how we would produce from a system like this. Now, this is an area in the Permian Basin, cleaned up a little bit, sanitized, let's say. So we have bed A and bed B. They are separated by 100 feet of shale. They are both fine-grained sandstones of similar thickness. Bed A here, after logging the core, about 150 feet of core, I believe, horizontal core along this formation, we look at a fracture set that are nearly parallel to each other, as shown by the rose diagram in the upper right. We look at the surface. It's a very planar surface and is mineralized, in this case, with barite. And these are extension fractures. So bed A is composed of very parallel natural fractures and extension fractures. Bed B was surprisingly significantly different. And we had about 130 feet of horizontal core, and there were two orientations of the fractures here. And if we look at the surface of that fracture set, down in the lower right, we can see some of these shear steps on here, indicating this is actually a shear fracture conjugate style set in strike slip mode, like the previous example we showed. So both of these beds have significantly different fracture types from each other, even though they appear to be quite similar just from looking at the core. Bed A has conceptually these very parallel extension fractures, while bed B has these strike slip conjugate shears that intersect. This has some significant production implications. And how would we test that in reality? And this was done. We did a tracer test. We had an injection well, and it injected both into bed A and bed B at the same time, crossed to a monitor well on the right-hand side. Now, from our previous discussions, we can theorize or hypothetically think about what we would expect to see. And in bed A, where these wells are parallel to the natural fracture trend, and they were, you might have a quick breakthrough from the injector well on the left to the producing well on the right. Whereas in bed B, where we have these conjugate intersecting fractures, they're going to be a much more widely spaced intersecting fractures that have a more wide path of fluid flow across them. So it's going to take longer for the fluids from the injector to go across to the producing well. And when we look at the actual tracer test, that is what we saw. So here's a summary of that. About 5 days out, we had a peak of the tracer come in, and we infer that's coming from bed B or bed A, and there was a very quick drawdown there. The tracer dropped off fairly quickly. About 20 days later, we began to see a second bunch of tracer come through, and we infer that to be through bed B, and that took a lot longer to actually sweep through bed B, almost 20 days. So here's a real world example from the Permian Basin on how these different types of fractures will influence production on those two beds. Now let's complicate the matter just a little bit and put in some intersecting extension fracture sets. Not every extension fracture reservoir only has one parallel set of fractures. Many times there's more than one, and many times they're of different scales. So which set is going to influence the permeability more than another? Well, several things come into play, and let's look at three of those. First, perhaps it's the most numerous set that dominates the permeability, so that we have the fracture set from upper left to lower right, which is much more closely spaced, would dominate that permeability with a little bit of influence in from the more widely spaced fracture set. That's one possibility. The second possibility is, what if that more closely spaced system, because it was moving fluids, became mineralized? And so now it's mostly closed to fluid flow, in which case that the set that has less mineralized will actually control and dominate the reservoir permeability. The third thing that could happen is that we need to look at the in situ stress anisotropy out here. The in situ stress, if it's fairly high anisotropy, could close off one set of fractures, the one that's nearly normal to the orientation of the maximum horizontal compressive stress, whereas the fracture set that is parallel to that maximum horizontal compressive stress will stay open. So the set that's actually aligned with the maximum compressive stress will dominate the permeability in this case. Now, I'm going to transfer this back across to John, and he's going to talk again about these different fracture types and some of the stress sensitivity of fractures and how hydraulic stimulations may interact with natural fractures.
Thank you, Scott. So Scott's been talking about the lateral connectivity and the changes that the different types of fractures provide in a reservoir. I'm going to talk about some of the vertical connectivity differences and as Scott said, some of the stress sensitivity. If you've got a set of extension fractures, it's very common that the fractures will terminate at bed boundaries. Here's a fracture coming down here. It basically terminates at the little interbedded shale. You can see that over and over again in this system. So if you have a layered system, you commonly have stratabound fractures if they are extension fractures. If they're shear fractures, however, that's a whole different story. These shear fractures, forming a nice conjugate set, commonly cut across some of these interbedded sedimentary heterogeneities in the system. So a set of shear fractures gives you a much better vertical interconnectivity within and across these reservoirs. What about fracture apertures? Extension fractures give you a very nice system of reasonably uniform fractures. Now, if you have mineralized fractures, such as this one on the left, yes, you still have some irregularities in there, but you still got a nice, reasonably good slot coming through there. Of course, if you've got dissolution coming through, as you have on the system on the right, things get pretty irregular pretty fast, but that's still a reasonably uniform fracture width and fracture aperture compared to shear fractures. Here's a shear fracture set. Both of these on the left and the right are shear fractures, and you can see how irregular they get. And you'll see up here in the top of this fracture system up, I've lost, there it is. That little tuft looks like grass growing out of the core. That's lost circulation material. It's probably cedar bark from 1948. They were having a hard time drilling this well because the fluid in the mud pits was being sucked up by the fracture system, and this irregular set of shear fractures and gives you a much more irregular set of apertures, a more regular trend along the apertures. And you can see that both on the left and then in the smaller scale on the pinch and swell type of shear fracturing on the right. So it doesn't take, this is only a couple of millimeters on the right. It doesn't take much in the way of shear to give you a significant offset. What about fracture face permeability? The ability of fluid to flow from the matrix into a fracture aperture. If you have a shear fracture, it's entirely possible, if you've got enough shear, to create a glassy, almost metamorphic surface. And that's a real permeability barrier. So a shear fracture can be significantly different than an extension fracture in the ability in allowing fluid to flow from the matrix into the fracture aperture. So again, it's important to know the type of fracture that you're dealing with in order to understand its effects on a reservoir. What about dynamic permeability? We're dealing with fractures in reservoirs, and they are not stable features. They're not uniformly, they don't have widths that are stable. Once you start changing the stresses in a reservoir, how do you change a stress in a reservoir? You start producing it. You start decreasing the fluid pressure specifically and first within the fractures, and then later on within the matrix. But that has an effect on the permeability of individual fractures. And it makes a difference. Again, if you've got an extension fracture, such as this fracture on the left, you've got a set of fractures that are typically parallel and normal to the in situ stresses. But if you've got a shear fracture, they are oblique typically to the in situ stresses. And if you've got a fracture that's oblique to the in situ stresses, you've got a critically stressed fracture. And now you've got the possibility of actually getting shear on the fracture as you change the in situ stresses. So what happens is, as you change the fluid pressure within a fracture aperture in an extension fracture, where it's normal to and parallel to the in situ stresses. Well, as you take a large width fracture, suck the fluid out of it during production, that aperture closes down, and then you start to reduce the permeability. You can see this in laboratory. There's several published papers. Larry Teufel did this one, and though you can see it in sandstones, you can see it in carbonates. As you change fracture width as a function of the confining stress, the permeability drops, and it can drop significantly. It can go from 100% to 40% in some of these units. Same thing happens in a limestone. So fracture permeability is stress sensitive. This is an example from the Piceance Basin in western Colorado, and it's a fluvial sandstone. And this is some work that Norm Orpinski did. And what you're looking at is initial reservoir pressure normalized to 1 in the horizontal, or in the vertical scale here, and pore pressure in the horizontal scale. And if you start in this initial condition and start to reduce the pore pressure in the fracture system, what happens? The permeability drops significantly, and the well is just about killed. If you start the other direction and start injecting into the system, this is not injecting above the parting pressure. We're not actually creating new hydraulic fractures. We're just opening up the existing fractures, and we can get 10 times the initial permeability by adding fluid pressure into the fracture apertures, opening up those fracture apertures. Fracture permeability is dynamic, at least for extension fractures. What about shear fractures? Well, let me show you an experiment. This was done by Bill Olson. He worked with Sandia National Labs with us. What he did was he took a cylinder and he put an artificial fracture across the center of it, and then he plumbed it so that he could inject laboratory oil. And he injected from the top the laboratory oil, and he measured the rate at which it came out, this artificial fracture. And he said, well, that's pretty good. I've got a permeable fracture. And then he said, let's shear that fracture. Let's rotate the top of the cylinder against the bottom of the cylinder. And he measured the rate at which that permeability decreased or increased as he rotated the two cylinders against each other, as he sheared this artificial fracture. And this is what he found. This is permeability on the vertical scale here. And on the horizontal scale, he's got the amount of rotation, i.e. the amount of shear in the system. And it doesn't take much shear to affect the permeability of that fracture, because this horizontal scale is measured in millimeters. And if you take this as the original permeability, and this lower line as the original permeability, he's got some strange units for his permeability, so I just took those off. As he started to shear it, permeability started to increase, which is what you would expect, because the apertures and the valleys and the asperities or the hills were beginning to be offset. So you're opening up this artificial fracture and creating more permeability along it. But as he continued the rotation, the permeability started to decrease. So we went from an increase in the permeability down, 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 and about here, when he'd lost about 75, or he lost about 25% of the original permeability, he said, gosh, I'm damaging the fracture. Let's see if we can restore it. So he changed the direction of rotation, and he went from one direction of rotation to the other direction of rotation, but the damage had been done. The permeability continued to increase. It got down to about half the original permeability, and then it stabilized. And we're not dealing with a whole lot of shear offset. Shear has damaged this fracture just because we've changed the fracture width during the shear. What about fracture type, the effects of fracture type on interactions with hydraulic stimulation fractures? Well, it's a kind of a big subject here, and there are companies out there that will quantify this for you, but conceptually, what we need to know is the natural fracture permeability. We need to know how closely spaced, how well developed the natural fracture system is. We need to know the cohesion of the fracture faces across towards each other, how well mineralized it is. We need to know the injection pressure, the fluid viscosity. We need to know something about the in situ stress differential, and we need to know the angle between the stress and the natural fractures, because the hydraulic stimulation fracture will approach the natural fractures at different angles depending on the stress control in the system. So let's just do a couple of quick thought experiments. This is plan view. We're looking down at a map view of an extension fracture system, and we've got several possibilities. In most cases, the maximum horizontal compressive stress is going to be parallel to the existing natural fractures, because that's the way they formed. But if the stress has changed since the natural fracture system formed, we could be in a situation where the horizontal compressive stress is at right angles or any number of oblique angles to the fracture system. So we've drilled a vertical well into this system, and we've put in a hydraulic stimulation fracture, and if the fracture fabric is parallel to the stress system, then the natural fractures are going to basically make use of the fracture fabric, but they don't always do that. The chord hydraulic fractures that people have looked at suggest that the hydraulic stimulation fractures don't always actually follow the existing natural fracture apertures. They're quite happy to break virgin rock, unfractured rock out in the reservoir. And again, it depends on how well mineralized your fractures are and what your compressive stresses differences are. If you've got a situation where your hydraulic fracture is cutting across the fracture fabric, you've got much greater potential for branching of your hydraulic fracture, especially if these fractures, the natural fractures, are reasonably open. They're going to suck off the fluids, the stimulation fluids. You're going to have the same situation where we had losses in the mud pit, and they were trying to eliminate or control the mud losses with the lost circulation material. In addition, every time you branch this system, you have a potential screen out for sand. You've got potential for pressure rises, and if you stop pumping, all these little jogs in the system are prone to closing up. And then you've got the possibility of losing a lot of your stimulation fluid and leaving a lot of your stimulation fluid out in the formation and getting poor recovery. What if you've got multiple sets of fractures? Well, as Scott showed you, it depends on which set of fractures is aligned with your stress, which set is most mineralized, which is most numerous, and which has the wider apertures. So you need to know something about an extension fracture system in order to be able to conceptually predict how it's going to interact with your stimulation fracture. What about shear fractures? Shear fractures are going to be oblique to the maximum horizontal compressive stress if they're in the strike slip system. And if you start putting hydraulic fluid pressure, hydraulic stimulations into a system like this, it gets very complicated very quickly. So we really need to know something about the natural fracture system, and at the basic level of understanding, we need to know whether it's a shear fracture system or an extension fracture system, because the lateral connectivity in these two systems changes. For an extension fracture set, as Scott showed you, the lateral connectivity is pretty poor. Shear, we've got much better lateral interconnectivity. Vertical connectivity, about the same thing. Apertures, extension fractures, you got pretty good apertures. Shear fractures, they're pretty irregular, but they have the potential of being widely open. How about the face permeability, the sigma factor of the fluid getting from the matrix into the fracture aperture? Well, again, it changes depending on whether you've got shear fractures, that could be slicken lines which completely inhibit fluid flow, or unmineralized extension fractures, in which case it could be very good. Your orientations with the stresses and the interactions with the stimulation fractures also change. So it's important to know what we've got in the system before we start making conclusions and start modeling it. So just in conclusion, the more we know about the fractures in the reservoir, the better, because fractures are the reality. We can have existing fracture types and they're not going to change. What we can change is the way we stimulate, how hard we hit the fracture system with pumping pressure, what kinds of fluids and what kinds of sand volumes we put into it. But the fractures typically control permeability, and we need to know something about them in order to say how they control permeability. If you can accurately characterize the fractures in the reservoir, you know how they influence permeability and isotropy in the reservoir. It will give you information on the vertical connectivity in the reservoir, and it'll give you some information on how stress sensitive these fractures are to production. So the bottom line is, if you're characterizing fractures, it's not wasteful science. You know, this is not a science project, and we typically get that thrown in our face. It's important to be able to present to management how we are using these important pieces of data to understand the production flow in a reservoir, how the fractures interact with the stimulation fractures, and what they do to the reservoir permeability system. So that's it for what we've got to present to you. Apologize for the preliminary glitches. I hope you learned something, and we'll turn it back over to the SCA people.
Great, thank you. We're starting to get some questions. I want to remind our listeners that they can address their questions in the dashboard using the webinar features, and if you can, possibly address your questions to either John or Scott. That would be very helpful. So the first question is for John. How can we effectively move the oil from matrix to fractures to improve recovery?
Well, the moving oil from matrix to the fractures, it depends on what kind of fracture you got, of course, which was the whole point of the seminar, webinar. But if you've got a high degree of mineralization, you can start putting some of the different acids into the system, perhaps to reduce some of that mineralization. If you've got a shear fracture with a lot of slicken lines and slicken sides on it, then you've pretty much reduced to the need to break across those with a stimulation fracture and break from the natural fractures out into the matrix with your stimulation.
Okay, now we're going to need to refer to your slide deck, so if you could bring that up, please. There's a question about slide 46.
Okay.
So if you could bring that back up, please. Thank you. I'm sure you haven't memorized every number of your slides, so let's go back to slide 46.
Okay, slide 46, we've got it up here.
Right, so the question is, what was the diameter of the rock in slide 46?
It was about a six millimeter diameter, or no, 6 centimeter diameter cylinder of rock.
Okay, thank you very much. So you talked a little bit about the when you have multiple sets of fractures, how the stress can be predominant, apertures can be predominant. How do you know which of the various factors is dominating in your fracture system?
Well, that's where you've got to have the basic data in order to be able to answer that question. You need to have some core or some image logs at least, or you need to have some kind of outcrop the analog. It's not an easy question, and you can't answer it in the absence of data.
And what sort of data program would you recommend putting in place for a thorough study of the fracture system in your field?
Well,
yeah. Yeah. Some of the FMI's awfully nice, you know. You end up combining an awful lot of data. You combine the core data, you combine what's available from seismic, you combine your well data, you know, what sort of interference patterns you're seeing. All of it together helps, you know, characterize the entire system.
The industry operates with image logs, and image logs are very important in this respect, but you need to be able to calibrate the image log signatures with a piece of core. If you can do that, you know whether the image log is giving you a true representation of your fracture system or not. And commonly, your image log undercounts the fracture system. But if you can calibrate the image log with a piece of core, the rest of that image log becomes much more valuable, and the image logs from the adjacent holes become much more valuable.
Okay. One of our listeners says, I've read your San Joaquin Basin paper. Do you have any thoughts about the orientations of fractures and orientations of horizontal Anka swells?
Ooh. Excellent.
Yeah, all the subsurface data that we have from oriented cores and from image logs suggests that there is a dominant north, northeast, south, southwest fracture fabric across the most of the basin, but locally superimposed on that, there is a northeast, southwest, even an east, northeast, west, southwest system that kind of complicates it. So it depends on whether you're close to some of these local structures, especially some of the basin margin structures, as to what your fracture system is going to look like. But those are the two thematic fracture systems across the basin.
Right. Yeah, because we're looking at an overall shortening direction from north to south across that basin, but there are local complications to it. And then the type of rock you're actually looking at, you know, is it going to be a little bit more ductile? Are we going to be looking at potentially some of these shear fractures? Or in the more brittle rocks, there are going to be extension fractures that will be more to the north-south orientation.
Mm-hmm.
So you remarked about the dynamic nature of these fracture systems. Is there any sort of surveillance that needs to be put in place during the life of a field to monitor the changes in the fracture system?
Well, pressure monitoring from these wells and production, you know, gives you some clues as to what's going on. I don't think that I'm qualified or that we're qualified to answer that particular question.
Right.
Yeah, that's in the realm of, you know, the engineers and what's what's available in terms of surveillance. But yeah, if you can perhaps be ahead of that curve and figure out what's likely to happen by knowing something about the geomechanics and the in situ stresses and your fracture system, in order to say, okay, these are apt to shear or these are apt to close down, whereas fractures that are oriented parallel to the maximum horizontal compressive stress and extension fracture set is not nearly as likely to be affected by the pressure drawdown.
Right, and some of this we go into more detail, obviously, in a 5-day class, but they can be very stress sensitive. So some of these wells, I believe it was Argentina, where they had some very deep wells and extension fractures. They opened them up and didn't hold any back pressure on them, and it actually collapsed the whole fracture system, and they lost production. Period. So. Some maintenance on these from the get-go is needed.
Right. Some fracture systems, like the Piance Basin, are elastic. So you can draw them down, they close up, and then you shut the reservoir in, let the pressure build back up. You've recovered most of your fracture permeability. But as Scott mentioned, others, you damage them. You shut them in, the formation closes in around the fractures, and you've lost it.
The next question, to what extent do rock compressibility and porosity affect hydraulic fracturing outcomes?
Okay, again, that's getting into the engineering realm. We don't pretend to be hydraulic fracture experts. We're primarily in the trying to understand the natural fracture systems, but the rock mechanics are very important. I'm flailing here.
Yeah.
So the next question, could you give us some examples of which types of EOR methods might be most applicable in the different types of natural fracture systems?
Oh, I don't think we're qualified to do the EOR types. It's knowing the locations and orientations of the natural fracture systems that allows you to design your floods so that they get maximum sweep, however. So if you know the fracture orientations, then you place your wells appropriately, your ejectors and your producers, and you get a better sweep in one orientation than you will in another orientation. In terms of the types of fluids you put in there, well, you want non-damaging fluids. In terms of the pressures you put in there, it depends on how stress sensitive your fractures are. So I'm dancing all around the answer here without actually providing one. But the fracture system is going to be dynamic, and we need to be able to design the stimulation or the EOR programs to accommodate that.
Thank you. What's your perspective on the reliability of natural fracture identification or interpretation using well log data?
It's important. The well logs provide information where we don't have information, but we're looking at a rock or a property of the rock. We're looking at a electrical property of the rock. We're looking at a sonic property of the rock. We are not necessarily looking at the fracture itself. We have seen instances where the image log overcounts the natural fractures in the system, not nearly as common as it is where we see the image logs that undercount the natural fractures in the system. We have seen instances where the fractures of one set are well represented in a image log, but of the second set that's oblique to or even orthogonal to it, it is not nearly as well represented. We have seen instances where the fractures are mineralized with pyrite and they just ring out great big boomers, but those are secondary fracture sets that are not nearly as important to the reservoir system as some of the others that did not have as good a signature on the image logs. So the image logs are invaluable, but we need to calibrate it, right?
Sure. We have time for one more question. Your 3 fracture types all appear with the same stress orientation. What other stress conditions will lead to one of the 3 fracture types?
Okay. The fracture type is dependent on rock properties. It's dependent on the pore pressure. It's dependent on the in situ stresses. It is dependent on stress rate. There is no one answer to your question.
In the example I gave from the Permian Basin, those 2 fracture types were formed under the same stress conditions. The only difference there were the actual mineralogical properties of the rocks themselves. Bed B happened to be a little bit more ductile than bed A, which was more brittle and deformed in extension fractures, where bed B deformed by shear fracturing. They are mechanically compatible fracture systems, and we see that based on those reservoir properties.
That's certainly very different results. So thanks for everyone who asked questions today in the webinar. You'll receive a link to a recording of today's webinar later today with an evaluation form. We welcome your feedback. You'll also have a link to the registration details for the course, Characterization of Naturally Fractured Conventional and Unconventional Reservoirs. That's scheduled for April 16th through 20th in Houston and October 15th through 18th in Midland, Texas. Thanks for joining us today.